Log on, tune in, find out. Another good idea from Cambridge.
I want to thank the organizers. I should say also that I have a confession to make. I'm not a mathematician, I'm a professor of mechanics. And I'd like to file a complaint. When registering for the conference here, you could tick what area you were working on, but even though it's the Newton Institute, there was no box for mechanics. So that should really be amended. Okay, as you can hear, I've got a bit of a cold, and at the end I will probably just show the slides and not say anything because my voice will be gone. And I also have a small confession that I have too many slides, so I'm very glad that this is being recorded, because you can then play it back at a slower frame rate afterwards and see what happens. My voice will then sound even more like Darth Vader's, but anyway. Okay. I should say that I've been out of research for a decade now, doing various managerial jobs, and but I got the chance to cease being a stuffed shirt and become a real person again recently, and I took up some contact I had with David Wall, who is a mathematician in New Zealand. He looks like that. And I should say, since I will be talking about invisibility cloaks, that what he is wearing is a visibility cloak, so you know that. Okay, I don't know if you can see this, but this is, according to David Wall, how the map is drawn when you're in New Zealand. So I went on a pilgrimage from Sweden to New Zealand and Christchurch to work together with him. What we were working on initially, and we published a paper on that also, was mechanical medical imaging, like the MRE, magnetic resonance elastography, and related to that, the kind of mechanical analog of the electric impedance tomography, the elastic surface impedance tomography. And we then naturally got into discussions about uniqueness for the inverse problem. And I should say that what we did work on, and which it was then for the ordinary equation of motion in elastodynamics with a stiffness tensor that satisfies both the major symmetry and the minor symmetries that you all probably know about. This is related to the existence of a strain energy function, and while these come from another source, and they are not independent, of course, these three. I'll say more about that later. And I should note that we were working solely with a scalar density. Now, to get at the problems that we saw with the uniqueness, if you look at an extremely simple 1D inverse problems in elastodynamics, you apply some force, traction on a boundary, you measure boundary displacements, and you want to determine the material properties and the thickness of a slab. It looks like this then, a simple 1D problem, very elementary. Then you can have a look at another slab that looks like that, with the different material parameters, and I've put a hat also on the coordinate here to keep things kind of organized. Is it possible to have these two different problems have the same Dirichlet-to-Neumann map, or rather, no, not Dirichlet-to-Neumann, it's traction to displacement map, I perhaps should call it. But that is in fact not, it is possible to have two different slabs with identical traction to displacement maps, as can be seen by a simple transformation of variables to between the two slabs, you can simply make the variable transformation, and this equation turns into this one. And then if you compare it to, divide down by that factor, then you can compare it to the equation you had for the other slab. And if you identify the material parameters, the mu, the shear modulus, in this manner, and the rho in that manner, then and the displacement in that manner, you see that you have identical problem. And if the transformation is the identity close to the boundary here at x equals 0 or x hat equals 0, you see that you have identical boundary data. So there's really no way of distinguishing between these two cases. Now, when it comes to mechanical waves, when we started talking about this non-uniqueness, immediately we found some paper suggesting that this kind of non-uniqueness could be very useful if you want to do other things than looking at medical imaging problems. And it was very natural to start talking about the possibilities of protecting infrastructure by using this kind of non-uniqueness. And that is, of course, something that was very close to David's heart. Just a few months after I left him, they had the earthquake in Canterbury, the first one, which shook things up. And after the second earthquake this year, David is no longer allowed even into the building where the math department is after the earthquake, because it might fall down on his head. So he was very motivated to look at these kind of infrastructural applications of non-uniqueness. So what I'm talking about is really, if we do look at horizontally polarized shear waves, and you have something that is buried in the ground like that, a tube of some sort, it is possible to set up a surrounding around this tube or whatever that allows the shearing waves to go past it without impacting it. And it's essentially the same thing as I showed you in the very simple one-dimensional example. Here I've written it in terms of cylindrical coordinates instead, and you do the same stuff again, variable transformation, of course. And when you have several dimensions like here, the anisotropy is essential, which is of course well known from the analysis of Calderon's problem for the electrical impedance tomography problems, where it was shown in, I think this is the first one, 2003, by Günther Ullmann and Alan Greenleaf, Matti Lassas, that really there is non-uniqueness for that kind of problem. And it's just a variable transformation between the two domains, and it can, of course, be utilized for hiding things, but then it's perhaps more interesting the form invariance that we have for electromagnetic waves that was published in 2006, Penry and Shurigan Smith. Very modest title, I should say, Controlling Electromagnetic Fields, when it really should be kind of hailed as the eighth volume of the Harry Potter series of books, because it's really puts invisibility cloaks on solid footing. And just to remind you, it's again this transformation optics thing. It's just a variable transformation where you transform the material parameters in accordance with the how the fields are transformed, and you get back the same equation, same Maxwell equations, but with different material parameters, and that can be utilized then for making things invisible. Now, immediately there was questions then, can you do the same thing for elastodynamics? And in the same year as the paper on the Maxwell equations and the non-uniqueness result there, people tried to do the same thing then for the elastodynamic equation of motion. And one would have hoped that one would get back the same equation, but one does not get that. You get not form invariance, but you get something that is a lot messier than the original equations. And that's a setback, of course. This analysis was in a paper by Milton, Briain, and Willis. It turns out that the kind of material that you get after the transformation was already suggested by Willis as a possible type of material, and it's discussed in this paper. It turns out that what you have to do is to sacrifice the scalar mass density, and they suggested a microstructure like this with small masses and springs with different spring constants around these masses in cavities in the body. Then you could get something that is equivalent to, if this is on the micro scale, and then you go to the macro scale, you get an anisotropic mass density. But they kept the symmetries of the elasticity tensor. Now, in 2009, 3 years later, then there was another suggestion by Brun and the co-workers on achieving control of in-plane elastic waves, where they instead sacrificed the minor symmetry of the elasticity tensor, but keep the scalar mass density. Then there have been a lot of other stuff going on when it comes to elastodynamic cloaking. Andy Norris is a great champion of the so-called pentamode materials, which can be used for at least acoustic waves. I should say that this is a very interesting type of material, but it has only one non-zero eigenvalue of the elasticity tensor, and as far as I know, nobody has been able to actually in real life construct a material like this yet. There is a good summing up of what is known about elastic cloaking theory. It covers in a unified framework most part of the elastic cloaking theory in the special issue of Wave Motion on cloaking that was recently published. I don't remember what, well, it's Wave Motion number 6, volume 48. And it's a paper by Norris and Shuvalov. But I say much of because it misses out one thing. The unified framework, which is really very nice. I should say a few things about it. In electromagnetics, the kind of transformation you need to do can be very easily determined if you look at the energy. And that's what they do in their paper. They look at how the energy is transformed. And you can, of course, get the equations of motions from a Lagrangian then, where you take the difference rather than the sum of the two energy terms. But they also stress very much that the coordinate transformation and the transformation of the fields, the displacement transformation, need not be the same. And that's a very good observation. If you do this, you realize that it'll become messy, and that you have there is a possibility that you get a non-scalar mass density. But by making various choices here, you can get either Willis material or kind of Kossora-like material with a scalar density. But I should emphasize this, that you sacrifice something in both cases. And this is perhaps better called a Coiter material than a Kossora material, because there is a difference. you know, because of our micropolar materials, you have a kind of internal degree of freedom. You can rotate things at a very small scale, but in the Coiter materials, you actually lock those two rotations to each other, the macro and the micro rotation. It's just that you have then terms in the energy function that contain also the rotation. Yeah, as I said, it missed out one thing, this general framework, and that is the fact that when David and I started looking at this, we realized after a while that fiber-reinforced materials, which is within the ordinary models of materials that are used in continuum mechanics, we can do kind of partial cloaking and keep the scalar mass density and all the symmetries of the elasticity tensor. But we pay the price then in terms of an internal kinematic constraint. But it turns out it is actually possible to have a body that we put forces on, static or dynamic, and it responds in such a manner that you cannot distinguish between a small hard core like that with fibers emanating from it and a case like this where you have a large core and an inhomogeneous cloaking layer around the center. I don't know whether the CIA would want to use this to hide a bomb or something, but from ultrasonic inspection, but it is in principle possible. And that means that we can add another line to this table here, that it is possible, if you use fiber-reinforced materials, to keep the symmetries and have row isotropic, so you don't have to have so fancy materials as had been suggested. Now, I'll skip the details of this, but I just want to show you it's the same. It's really the same thing as the original 1D problem I showed you. You just look at the equations of motion. I should say that the difference here then is that you have an extra term here containing a Lagrangian multiplier, and A here is not the what it was earlier. This is just a constraint matrix that picks up the direction of the fibers, and here's a 2D case. If you look at the equations of motion, you have two components in that. And if we focus on one of these, the one containing the rho term here, then it is simply, you have a transformation between these two situations. You transform the fields like this, the tensor of elasticity like this, and then everything works out nicely in that case. It's exactly as in the 1D case that I described, works beautifully. But then we look at this equation and try the same transformation there, and it doesn't work. It just gets a mess, that equation. But as I said, the P is just a Lagrangian multiplier, so we don't need that equation. We just need an expression that works as a Lagrangian multiplier in this transformed problem. And that is very simple to put up, and we can make sure that it satisfies the right boundary condition also. So we take the equation that we can transform, throw it out the window, and write down the equation we want, just to get the P, the Lagrangian multiplier that we need to solve the problem. And then it turns out that these two together are then a solution of the transformed problem. And in the usual manner, you can do a cloaking then. I don't know, how many minutes do I have left? 10 minutes, okay. Wow, okay. You mean? Oh, okay, but remember what I said about the frame rate when you look at the recording. Here is an example. I won't go into the details of it. It's I looked at what happens. The mathematical analysis that we had done was really for, whoops, oh. Do you have a fly swatter? I can. Okay. I was going to say that of course, the mathematical analysis is done for a model of the fibers as perfectly inextensible, which is unrealistic, of course. So I did calculations for instead rather stiff fibers. I wonder whether that fly is bugging me all the time. Look funny on the video there. Okay, I did calculations for fibers which were in fact elastic. It was very simple in COMSOL multiphysics to do this kind of modeling, and I looked at some 2D and 3D problems comparing a small inclusion in a homogeneous matrix with radial fibers to one where we have a cloaking layer around a much larger inclusion, and one where we have the same inclusion but homogeneous matrix and the fibers around it, just to have something to compare. How well did this layer then cloak the inclusion? And I also went to a vanishing inclusion at the center, just point really, and applied some forces along one part of the boundary of this object, and then looked at the fields on the boundary, the displacements as a result of that force that was applied. And well, you can probably not see it, but there are actually two curves on top of each other most of the part here. There are some small differences there. This was at frequency of 15 kilohertz, and the size of this thing was 0.2 meters. And actually, if you look at the pattern, this is for even higher frequency, 25 kilohertz, you see that there's a huge difference between the field, you can't really see the details here, in the uncloaked case, but with the cloaking you get the field at the boundary very close to the field you have in this case. So it's possible to achieve. Now this was 2D. You can do it in 3D also. In this case I applied at this quadrant some force, some traction. I don't remember exactly what it was now, but it is in the paper I stated. And you can compare the uncloaked big inclusion, the cloaked big inclusion, and the small one. And you see that it's very close, and very large difference to what happens with the uncloaked one. Now you can also use this in scattering problems and at least get rid of a lot of the field. This is a rigid sphere, much heavier than the surrounding elastic material. We send in a plane wave, and we get oh no, I don't remember the frequency here, but the point is really that you get a big shadow region here, and you get scattering from that rigid sphere. If you coat it with a fiber layer with the right kind of material properties, and even allow this layer to rotate, put it on a kind of, well, rotating shell around here, then you can get rid of much of that. It becomes effectively transparent for most of the shear waves that goes through. And let's see, in this case you have a cloaking layer that is not allowed to make rigid body rotations, but just cloaking, and it's almost as good as the rotating case. Here are some differential cross sections for uncloaked sphere, cloaked rotating, cloaked non-rotating, and this part is what you get if you artificially subtract the shear wave scattering part of the scattering cross section here. So you see, this is much better than just subtracting the shear wave part. It actually takes care of a lot of the P wave part also. Yeah, this is impossible to see from where you are sitting, so I won't say something about it. We had a motivation for, we have the earthquakes in Christchurch. In Sweden and in Gothenburg, we have these problems with the high velocity trains. I should mention also the fact that we can, the Swedish high velocity trains, they run on the already existing ordinary tracks. And that poses a big problem. Because you can then have buildings that were erected close to the tracks that are affected by the ground waves emitted as a high velocity train passes, and that's really a problem. That so I looked also at the two-dimensional problem. Is it possible to kind of get waves if you send in an elastic waves towards a fiber layer like this? Can you make the reflections become rather small, and can you get the wave as it enters the layer to mostly move along the layer, so you can let it out somewhere where it won't make the bookshelves topple over in the buildings that are too close to the track? And it turns out that this is indeed possible to do that kind of cloaking also, which might be interesting. I'll skip this one. This is just a similar comparison for the planar case. So I think I'm finished. I see some people that show very bad signs of having too low caffeine levels in their blood, and so I guess it's time for questions.
Well, any questions?
Have you given any thought to what you would do if you wanted to detect that cloaking was inside an object?
Sorry, to detect the
cloak.
Yeah, in this case, for, as I said earlier, or maybe implied, that when it comes to mechanical waves, except for the CIA and Al Qaeda and stuff like that, it's not really about making things invisible. It's more about protecting things from unwanted waves. And of course, you could say one thing if you were looking at the case I had somewhere here. Yeah, that one. Oops. That's it. If you looked at that and made a reconstruction using some kind of optimization, and you realized, oh, there's a lot of fibers in there going in strange directions, I would become suspicious and cut the thing up or use electromagnetic waves to look at it. But really, I haven't looked at detection from any other point of view of it, but definitely become suspicious of the fact that you reconstruct something with strange fiber directions.
Is the fibers and the internal geometry, is that for a single frequency?
No, it works, at least in theory. You should say like this: as long as you respect the length scale of the continuum of approximation of the fiber material, so you can use. You don't have to look at the individual fibers really, but you have a continuum model. As long as you respect that, you can do it in the time domain. And actually, the results on when it comes to the application of trains going past, it's in the time domain, so it works. Yep.
Would you be able to design your cloaking device based on certain sources then? So it may be absorbing the train noise, but not necessarily like a heavy truck?
Sorry, I didn't...
Be able to, possible to tailor your cloak based on a source. Not necessarily an earthquake or a train, but say you had an earthquake and a train at the same time, but you would only cloak the signal from the earthquake, but you still...
Well, as I said, at least the models we've had so far are it works at all frequencies. So you would have to have some other way of distinguishing between different frequencies of the waves, I guess. Or maybe polarizations will be different, and that you perhaps could utilize to make such a distinction.
Take one more question.
In clocking elastic waves, there are some difficulties as they compare to electrodynamics. Now, do you think that this is due to the fact that the different elastic waves are uncoupled, or to the fact that they have different phase velocities?
Well,
I mean,
I'd go for the velocity because of the fact that, I mean, if you look at what you really want to do in a cloaking, then you have a wave coming in and you want to take a different route so that it comes out at the same time as waves that had passed on the side of the object, so as to have an undisturbed front. And you really have to get all the waves to change their velocity in a coherent manner for that to happen.
yeah, thank you.
And actually in the 3D case, and also 2D, you have here both more pressure-like and shear wave-like waves going around, but in such a manner that they come out. But the fibers are really necessary, because if you didn't have the fibers, then you would get one wave that didn't get there on time, so to speak. So I'd go for the time explanation.
Okay, let's say thank you again.
Thank you.